or not. But that's the definition, right? It's the limit as h approaches 0, blah, 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 blah. That's the definition. But what, like if you create a derivative function, what is it doing for you? Okay, so yeah, it's a pretty good way to put it. So you have a function now, so you have an input place for it, x, that when you put in the x value, you are producing, that function is producing the slope of the tangent line at whatever you plug in there. Okay, and so that's like when we're looking, you know, if we're still looking over here, like what is this slope, positive or negative?
Negative.
It's negative, right? So then all of the value of, so for the derivative function, all the values you would plug in here, like around -2 to -1, are the outputs of your function that you created are all going to be negatives. Now they're not very big negatives over here because this is almost horizontal. So this would be like, these would be like, you know, 1/2, 1/3, 1/4, things like this. And then all of a sudden, like right around here, it's like that starts, so negatives, sorry, -1/2, -1/4. Right here, then it's like -1, and then all of a sudden it drops off the cliff kind of thing. And so then when you're putting in numbers like -1.001 into what you would have created, then it would be outputting like -500, -10,000, -50,000. Okay, and so that's why, like it, you know, that's why you're paying attention to the slope, because that's what the outputs would be. All right, so everyone, I want you to try to sketch this on your, like on a piece of paper. See what you come up with. I'll give you a second here. And just to make sure we all understand, well, how many places is your derivative going to cross the x-axis? One. Only once. Okay. So if you're not sure, like, where you're starting, I would start with the middle one, because that's where it should be crossing the x-axis, right? Okay. All right, that's where it's crossing the x-axis. And those should be the easier types to do, is where it actually is giving you a tangent slope of 0. So you think we got something? No.
The middle one.
Just the middle. Okay, so then the middle one, let's do the middle one then. looks to me that it's crossing like right about there. Is that about right? Something really close to that. All right, so then let's look from, like, let's start here at the asymptote and come down to where it's 0. So what kind of slope is this? It's negative. So is that part going to be above or below the x-axis? Below. And so if you really want to get really specific, super steep, so very, very negative, right? And then as we get closer, it's getting closer and closer and closer to 0. But it's, super steep, and then it starts slowing way up. So then, it's going to look, and it starts slowing up, and then, well, kind of my hand just jumped. Right, and so then from that point, does the slope change to something besides negative? It does change to positives here, okay? It doesn't have to, but like it does on this one. And so then for the rest of this middle part, should be above or below the x-axis? Above, because now we're getting positive slopes. And it's kind of doing the same thing, right? It's kind of very slowly, it's positive here, but very slowly. And then all of a sudden it takes off, kind of like right here, it starts really taking off. So you could kind of, I'm going to miss it, but like, oops, I'm going to try to hit it. So then it's kind of slow, and all of a sudden it's like taking off again. All right, so is that part okay? Okay, does anyone think they know let's do the left one first. Does anyone think they know what that's looking like? Okay, so do we recognize this as always negative here? Okay, so then very small value. So again, it's always negative up until this asymptote. So then all of it should be below the x-axis, right? Okay, so then very flat, so the slopes are very close to 0. So our derivative is going to be very close to the x-axis here. Okay, because it's very flat, producing very small slopes. And then all of a sudden it drops off the cliff here. And so then it's going to produce more and more steeper or further away from the x-axis as it goes. So actually on this one, it's basically just this. Does that kind of make sense? Okay, so then the right one, very similar. It's all below because it's negative everywhere. But it's kind of the same, but like real close to the asymptote, it's very, very steep. So that translates into very, very far away from the x-axis. And then as we come down, then we start slowing down and it starts to flatten out. So the slopes become smaller and smaller, still negative, but getting closer and closer to the x-axis. So then it's going to look kind of like this. Is that okay? So it's weird. It's like weird to think about this, okay? And now, today's going to be the last day that we kind of play around with this idea. And then all of a sudden, it's like we start doing a lot more mechanical kind of, like what you would, consider like you're just doing math problems here. We're going to do that for a long time. And then the worry is that you forget that this is what we're talking about. Because you're going to start getting a lot of just like graphs. And what they do is say, okay, here's f, and then on another graph, they don't put it on the same graph. On another graph, they say, oh, here's what f prime looks like. And then you got to know which one you're supposed to be looking at, and then, and you haven't done this for a while, so it's like, oh yeah, what is all this going on? So you really got to try to keep in mind how the graphs relate, okay? So was there any other ones that we need to look at, or does that make 13 okay now?
Yes.
Okay. All right, so then not a whole bunch more today no, I don't want that. Not a whole bunch. But there are some important things. Here's the answer, so, right, that's basically what we did. Oops. So we come back to this continuity thing. And we have this theorem, and this theorem is going to kind of explain a couple other things for you. Okay, so if we can say that this function is differentiable, and so, well, let me explain this. At this point A, then it is also continuous at A. Okay, and so like if you think back on the free response stuff that you guys did, they would ask something, like they would check this knowledge by asking you something to the effect of prove, or well, not even prove, show that this, so they would start out saying like, you know that f is differentiable. Show that f is continuous at 3. And so then what happens is you go, oh yeah, that's the checklist. But then you don't have any information about the checklist because they give it to you on a table or they give it to you on a graph, and you're like, but how do I want to go through my continuity checklist and I can't. And so then you have to go like, oh, it's continuous because you told me it's differentiable everywhere. Okay, so that's kind of the ways they kind of do this kind of stuff. So if you can take the derivative of it at a point, then you know it's continuous at that point. If you want to look at the proofs, like some of the proofs are pretty cool. This one's kind of obnoxious. I'm not doing proofs with you guys. Like if you go really far in math, like what ends up happening is you take a bunch of calc and then you take a bunch of other classes, and then toward the end, and this is what I did, like then you take something called advanced calculus, and it's just doing proofs for everything. And so like it's pretty intimidating. So my point is we don't need to worry about that. All right. So then they talk about, well, that's still the proof up there, okay? So over in this little pullout, they talk about the contrapositive. So this is just like for a little bit of knowledge. I think it makes sense if you read it this way. A statement and its contrapositive are two equivalent ways of expressing the same statement. And then they say, if I live in Denver, then I live in Colorado. And then that's equivalent to the contrapositive, which is negating both of them and rearranging the order. So if I don't live in Colorado, then I don't live in Denver, right? So that makes sense. And so then over here, they kind of done a contrapositive. It says if f is not continuous at A, then f is not differentiable at A. Okay, so then that ends up being very important. So then, coming back to our continuity checklist, you could be asked to show that this is differentiable at A, and then you would have to do your continuity checklist, and you would say, oh, okay, so by the continuity checklist, look, it's continuous, so then therefore I know that it is possibly differentiable. And I say possibly because then down here they say, don't over-analyze this. Just because it's continuous doesn't necessarily mean that it's differentiable. And then we start talking about the stuff that you guys kind of brought up yesterday, right? So here's the first one. They say, hey, look, if you come to this little cusp, or I don't know if this is a cusp or a corner, right? It's too dramatic. Like you need it nice and curved. So you'll start reading things like smooth. Things have to be smooth for it to be differentiable, okay? And then, so then they give you the other two. That's the cusp. The thing on the left there is the cusp. Okay, so it's kind of the same kind of idea. And then a vertical line, right? You can't take a derivative out of a vertical line either. So then they give you another checklist. Okay, so a function is not differentiable at A if at least one of the following conditions is true. Why does that keep happening? F is not continuous, okay? So again, if you just say, no, it's not continuous there, can't take the derivative. If it has a corner or a vertical tangent, like that's the cusp and the absolute value, think of absolute value. All right. All right, so what I think we should do, because you'll see stuff like this occasionally. Is this good? Can we do this? as the following features. Oh, and then they do it to off to the side. You're going to see a question like this occasionally, okay? So they like doing that kind of stuff. But for the most part, like that's what I got for you. So, all right, so find the values of x in 0 to 3, the interval 0 to 3, at which f is not continuous. So just one. What about the values of x in 0 to 3, that interval where it's not differentiable? 1 and 2, because you can't do it because of that like little check mark. All right, so then sketch a graph of f prime. I'm going to have to give me a, let's see, we'll do it over here. All right, so then is up from 0 to 1, is that going to be above or below the, it's going to be below, no, why would it be below?
Because you're like, it's like negative times.
Well, we're doing f prime now, so isn't that a positive slope? Okay, so it should be above the x-axis. Okay, so then, it starts off kind of flat. So kind of flat and then gets a little steeper, so then it's maybe like that. So not much different. And we'll put an open circle right there. Then from 1 to 2, what's it going to do? Or where is it going to be? It's going to be below because those are negative slopes. And again, it's very flat at the beginning. And then, so I'll put it kind of closer. And then it kind of goes away to 2. And then I guess it depends on how you read from 2 to 3. So is it above or below? Above, that looks kind of like a linear to me. So then what kind of line am I going to draw? Yeah, horizontal. Okay, so then I don't know what is that, up, looks like up 2 over 1. So like maybe like right here. Is that okay? So, you don't know what these are. And so don't fall in love with thinking that oh, that's a parabola or whatever. So what they're saying is like, so this is kind of a parabola. And so if you think about, if you remember the one thing you guys discovered yesterday, right? A constant, the derivative would be 0. And then a linear, the derivative would be a constant. And then if it's x squared, the derivative would be linear. So like if they're saying that those are linear in the back, then like what they're saying is like that's basically an x squared. Okay, and so then they're saying, okay, so then this is positive, so instead of this, and like, if I'm grading this, I'm saying like if you do this, this is fine. But so like they're saying, oh, well, that's really a quadratic, so that should be straighter. And then they're saying that's really one upside down, so that would be straighter. Okay? What I was putting in there was that it was more like a cubic. But there's nothing that says that it isn't. So like, you know what I mean? Like, the important point is that you understand that it's not a constant. How about that? Okay, that you know that there is some change in the derivative, it's getting further away, it's not staying constant. Okay, like that third one was obviously constant.